Greetings everyone. So today's episode is about capacitors. Capacitors are electrical devices, circuit elements that you'll find in pretty much every piece of electronics you'll ever use. For example, here's a circuit board. There it is, you can see it better here. So these things over here, that's a capacitor over here. Those little green things, those are capacitors. The red thing that you have over here, that's a capacitor. So as I mentioned, you'll find capacitors everywhere. So let's start from the basics and understand what is the phenomenon of electrical capacitance and take it from there. So life is filled with stuff and the stuff has to be stored. Look at this warehouse over here. You have boxes stacked on top of boxes on top of more boxes like this. Every time you stack up a height, you have potential energy. You may recall that the gravitational potential energy is mgh. So the more the height, the more the potential energy. If you have more potential energy, you need to do more work. Who wants to do more work? So instead, if you had more real estate, more space in your warehouse, you could basically stack the boxes horizontally. Then you have less potential energy, less work. More important, you avoid the risk of falling from a ladder and breaking your neck. That's the idea. So in the same way, you need to store charge economically. Economically as in with less potential energy. And that's what capacitors are about. They let you stuff charge without raising the potential energy excessively. Why do you need to store charge? For example, in the case of a defibrillator. So if you have a patient whose heart is misbehaving or has stopped altogether, you shock them and hopefully the heart will be restored. The rhythm will be restored. And that's basically what a defibrillator is. So on any of these machines, you have a great big capacitor that's charged to a certain voltage and with a certain amount of energy in joules. And then you basically apply those paddles to the poor patient and hope for the best. So let's now look at the stuffing ratio of how much charge you can put on a sphere for a given amount of potential energy. So if you put charge on a sphere, these positives are basically repelling each other. So there's potential energy, there's tension. It's like a compressed spring. So in a previous episode, we saw that the potential energy for a spherical distribution of charge is kq over r. Now let's say you stuff that same charge into a smaller sphere. This one to the right over here. So you have the same amount of charge squeezed onto a smaller sphere. As soon as you do that, those positives are closer together. They're going to repel more strongly. You have a higher potential. That's why the formula, the V equals kq over r, the r is in the denominator. The smaller the r, the more stuff the charges are, the higher the potential energy that you have and potential. And the potential energy, that's equal to the charge times the potential. Because the potential is varying, you have to take an average. That's where the half comes in. The details of that we'll discuss later. But the point is, you have less potential energy and less potential, a lower voltage if you have a bigger sphere versus a smaller sphere. And so this is similar to the warehouse situation. If you have more real estate, the boxes are spread out to a lower height instead of climbing to greater height, you have less potential energy. So similarly, if you have more real estate over here, a bigger sphere, the charges are farther separated, less tension, less potential energy. So this quantity, the ratio of the charge over the potential, this is defined as the electrical capacitance. So that's similar to the situation in the warehouses. If you have more real estate, you can put more stuff in there without increasing the height a lot. That's why the potential, which is like the height in the case of gravity, that's in the denominator. The more stuff you can store, in this case charge, not boxes, it's in the numerator. So the ratio of Q over V gives you a sense of how much charge you can store for a given potential. And that's called the electrical capacitance. The symbol for that is a capital C. And the unit for capacitance is a farad, symbolized by a capital F, in honor of Michael Faraday, who worked on the electrical stuff. Next, let's calculate the capacitance for a spherical capacitor. So if you just have a sphere, how much charge can you put on it for a certain voltage, for a certain potential? So C of the sphere, the definition of capacitance is Q over V, the charge per potential that you could put on there. In the particular case of a sphere, the potential is KQ over R. So Q over V is a Q over KQ over R. The Q's cancel. You end up with just R over K. So a spherical capacitor has a capacitance of R over K. So as you would expect, the bigger the R, the bigger the capacitance, more real estate basically. And the factor that connects the proportionality is this K over here. This K is your familiar Coulomb's constant. Next, let's do a numerical estimate of how big a spherical capacitor has to be to have a capacitance of 1 farad. So C of the capacitor from the formula that we just derived is R over K. You want that to equal 1 farad. So let's put 1 over here for the value of the capacitance. K is your 9 times 10 to the 9. So R ends up being 9 times 10 to the 9. So think of how big the capacitor is. For a spherical capacitor, the size is bigger than the size of the sun just to get 1 farad, many times bigger than the sun actually. And similarly, if you have, instead of a sphere, a flat piece of metal, once again, for a 1 farad capacitor, the size of this is basically crazy. It is out of control. So this is not the best way to store charges compactly. So there's got to be a way to raise the capacitance without making the size of the solar system basically. How do you do that? So here's a thinker question for you. Think of a design that's more compact. So if I have a plate of charge, here's a positively charged plate, for example. These positives are repelling each other, you have potential energy. As you saw, if you want a 1 farad capacity, be able to store 1 coulomb at 1 volt, this thing becomes larger than the size of the sun. So what can you do? Think of a design by which you can reduce the potential energy and so the potential, the voltage, while being able to store lots of charge and without making this crazy big. So think about this for a second, and let's reconvene shortly. So here's the solution. You have a positively charged plate. These positives are repelling each other, creating potential energy and tension. Bring a second plate that's negatively charged close to it. That's going to attract these positives and hold them in place, make them less frantic and less anxious to get away from each other. This is the way to reduce the potential energy. So on the figures over here, here's the positive plate. You bring a negative plate close to it. This kind of a view of these plates in front of each other. And the more the area, the more the capacitance you're going to have. That you would have anyway if you had a single plate or a single sphere. But by bringing 2 plates close to each other, which are negatively charged, you reduce the potential energy. You add attraction where there used to be just repulsion. So the formula, you expect the capacitance to go up as the area goes up. That one is obvious. But also the capacitance will go up as the distance between the plates decreases. So holding them like this so far away, it's like you might as well not even have this. As you bring it closer, these negatives will reduce the repulsion of those positives and hold them in place. And when you do the actual derivation, a story for another time, you find out that this C is proportional A over D, and the constant of proportionality is 1 over 4 pi K, where K is the familiar Coulomb's constant, the 9 times 10 to the 9. Now this group of quantities that you have, the 1 over 4 pi K, what's in the parentheses over here, this occurs often enough in formulas that's worth giving it its own name. You can abbreviate this whole 1 over 4 pi K by epsilon 0. So this epsilon 0 has the value, is basically 1 over 4 pi times 9 times 10 to the 9. That ends up being 8.85 10 to the minus 12. And this constant has its own name. It's called the permittivity of free space. And why is it called permittivity of free space? Because there's a permittivity of space that's not free, where there's other stuff in there, not a vacuum. So to quickly summarize, if you have a single plate and you put charges on there, they are stuffed, you create potential energy, you create potential, lots of it. So if you want to store a coulomb at 1 volt, you require something that's basically the size of the solar system. However, you can bring an oppositely charged plate, a negatively charged plate over here close to it, and that holds the things in place, and therefore it reduces the potential energy. You have more capacitance. That's a parallel plate capacitor. Exactly how much is the value of the capacitance? That's given by this formula over here. You have the 1 over 4 pi k A over D. 1 over 4 pi k is abbreviated as another constant, epsilon 0. That greatly simplifies the equation, makes it much better looking. And this epsilon 0 is the permittivity of free space. That has the value 8.85 10 to the minus 12. Now, one way to boost capacitance is through dimensions, larger area and having the two plates basically close to each other. But having done that, there's a further step one can take to boost the capacitance even further. Remember, increasing capacitance is about reducing the potential energy, reducing the potential. It's like the warehouse with more real estate. You can have more boxes without raising the height. So this second thing that can be done is to put what's called a dielectric between the plates. So let's say you have two metal plates. You brought them as close to each other. You made the area as big as you possibly could. On top of that, if you put a piece of plastic like this stuff over here in between the plates, here we go, something like this, like the sandwich. This has dipole molecules inside. It has dipoles inside. Those move around, they reorient with the electric field, and they reduce the electric field inside. How that happens is in the following way. So look at this diagram over here. This plate is positive, this plate is negative. You have a certain capacitance. But on top of that, if you put stuff in here which has dipoles, those dipoles, remember the electric field is pointing from the positive towards the negative. So that's the direction of electric field. If you put a dipole in there, it's going to feel a torque. It's going to align with the electric field. So what ends up happening is with the dipoles, the negative end of the dipole faces the positive, and the positive end turns towards the negative. So it's as if this negative charge was basically brought over here. It's brought closer. That's like reducing the distance between the plate. If you reduce the distance, you're going to boost the capacitance, because from the previous formula I had over here, the closer the opposite charges are, the less the potential energy, the less the capacitance. So by putting something in here which is dipoles that can rotate, and so that the negatives face the positive plate and the positive ends face the negative, that's going to basically lower the potential, is going to lower the electric field. And by how much? By a constant called the dielectric constant. So this thing over here, it looks like a K. It's actually a kappa, which is basically a Greek K. But this thing, this constant here, it's called a dielectric constant. So you have a boost in the capacitance by a certain factor. You would have had a C0 with this previous formula that you had over here. If you had nothing in there, free space, if you put some stuff in there, like the polystyrene or any other kind of plastic, that's going to reduce the electric field by a certain factor, and you have a C which is enhanced over the C0 that you had when you had the empty space between these things. And this gives a modification to the previous formula. So previously you had epsilon 0 A over D. Now you have a boosting factor, the kappa. This kappa can be absorbed into the epsilon 0. So you have a new epsilon without the 0. This epsilon is equal to the kappa times epsilon 0. So this is the kappa times the epsilon 0. And this is called the permittivity, not a free space, permittivity with the stuff in there. So here's a quick summary of what we just discussed. You have epsilon is equal to kappa times epsilon 0. Epsilon 0 is the permittivity of free space. That's at 8.85 10 to the minus 12. If you multiply that by kappa, if you put some stuff in there, a dielectric, which is another name for an insulator, then the dielectric constant kappa modifies epsilon 0. and gives you epsilon. So this is the permittivity. And these letters, by the way, this is a Greek letter kappa. This one is an epsilon. So here are some example values, some sample values of the dielectric constant. So this again, this is the dielectric constant. So a vacuum is 1 by definition. You have the permittivity of free space. And air is very close to it. It's almost 1. But then you put other stuff in there like mylar, tantalum pentoxide, aluminum oxide, etc. You have a boosting of the capacitance because it reduces the electric field. So here's a little mylar capacitor, by the way. That's what this baby looks like. Now a new kind of problem arises when you put a dielectric between the plate. So here are my negative and positively charged plate. Instead of having air, I put a dielectric between them. As soon as I put a dielectric, there is now stuff between the positive and the negative plate. So if I apply a large enough electric field, this thing breaks down. So what do I mean by that? So we talked in a previous chapter the difference between insulators and conductors. In conductors, you have mobile electrons that can move and carry electricity. In the case of an insulator, the electrons are all sort of bound in place. They can't move, they can't flow like a liquid basically. However, if you apply sufficient force, a sufficiently large electric field, you will tear those electrons free. They will start to move, and an insulator turns into a conductor. So if you apply too high an electric field, this thing breaks down and becomes a conductor. So you have to make sure on the capacitor, the two plates that you have, the positive and negative, the voltage and electric field does not exceed a certain amount. Otherwise you'll have breakdown. You have conduction and the capacitor will short itself. And this is what happens even in the case of air. So air is an insulator, it's a dielectric, but if you put enough electric field, you have a spark. The electricity basically jumps across, the air becomes a conductor. You see, so much for air being an insulator. So this brings about the concept of the dielectric breakdown, the electric field that basically makes the insulator turn into a conductor. So every insulator has its limit beyond which the electricity will basically jump through and force it to conduct. So for air, it's 3 million volts per meter. So that Van de Graaff generator was throwing 4-inch spark. In fact, if you don't have that little sphere close to it, it can throw almost 1 foot long spark. So that's about 1 million volts. That's how high that thing goes. Tantalum pentoxide is much more resistant. It's 526 million volts per meter. So air actually breaks down more easily than some of these other things. A diamond is a whopping 2000 megavolts per meter. So it's 2 billion volts per meter. Now let's get back to the mylar capacitor. So for mylar, the breakdown electric field is 250 million volts per meter. And then the dielectric constant we saw earlier was 3.1. So instead of having empty space of just air or vacuum, if you put mylar in there, you have 3 times as much capacitance because of those dipoles reorienting themselves. However, now if you put too large an electric field, anything more than 250 megavolts per meter, that thing will break down and the capacitor will not remain, the plates will not remain insulated. So let's now do a numerical example for how you design a capacitor. So if you feel prepared already, if you want, you can pause the video and do this before you see the solution. But the question is the following. You have a mylar capacitor like one of these things over here, and you want it to have a 2 microfarad capacity, a capacitance, and the spacing between the plates is 20 microns. So the question is, how big does the area have to be, and what's working voltage? So you want the area to be such that for this spacing here, this the distance between the plate, you have a value of 2 microfarad. But that's because you have some dielectric in there, there will be a maximum voltage that you can charge it to. And what is that working voltage? What is the maximum voltage? So here's the solution. The value of the capacitance is equal to kappa epsilon 0 A over D. If you had nothing in there, just free space, you would not have the kappa. Since you do have the molar in there, you have the kappa in there. So this kappa is 3.1 for molar. A is what you're trying to find, how big that the plate area needs to be. The epsilon 0 is 1 over 4 pi k. The k is 9 times 10 to the 9. And then the spacing between those plates is 20 micron. So it's 20 10 to the minus 6 meters basically. So make sure you convert all the units to our standard form, the MKSA units. So having done that, rearranging this equation gives you A. So A is equal to all of this, the whole thing rearranged, 4 pi k d c over kappa. C is the capacitance over here, d is the spacing, little k is the Coulomb's constant that came from there, and this k, that's the dielectric constant. That's the thing that's 3.1. So filling in the numbers for that, you get this. Crunching it out, you get an area of 1.46 meters squared. So even for a relatively modest capacitance, that's 2 times 10 to the minus 6 is 2 microfarads. It's not a big capacitance. You still have a huge area, 1.46 meters squared. That's a lot of square feet. So as a result, what's done is you have these two plates, like here's the one plate, here's the other metal plate. You put your dielectric in between. You basically stack them up, and then you roll these into a cylinder. So roll the thing like a Persian rug, and that makes for a more compact design. And this is one of the reasons most capacitors that you'll see, they're cylindrical in shape. That's because you have two foils with an insulator in between, and then the whole thing is wrapped up to form a cylinder. Hence the common cylindrical shape for a capacitor. So for the next part, we want to find the working voltage. What's the maximum voltage at which this capacitor can be used safely, basically. So if you buy any capacitor, you'll notice not only does it mention what the capacitance is, in this case a 10 microfarad, it also measures the maximum voltage, 400 volt. So that's called the working voltage, is the maximum voltage beyond which the thing will basically get fried. The capacitor will be toast. So we want to calculate the maximum voltage for our molar capacitor in the problem. So we already found how big the area of the plates needs to be to give you this capacitor. We want to find the maximum voltage. So the breakdown electric field for molar from the previous table, it's 250 megavolts per meter. So beyond that, you have a breakdown. That's what the BD basically stands for. Now the electric field is related to the voltage, to the potential difference. From a previous episode, you may recall that the E is the gradient of the potential. So the electric field is delta V by delta R. Here we are not concerned about the signs. When you say the capacitor is holding 12 volts, you're not really thinking about the sign. It's just the magnitude. So the magnitude of E is the magnitude of delta V by delta R, the gradient in the potential. And this delta R, the plates are separated by distance D. That's the D over here. And then EBD is 250. Because we have molar, the maximum E that you can have is 250 megavolts per meter. So when you crunch this thing out, the delta V, the maximum voltage you can have between the plates, before you have that spark, like you saw with the Van de Graaff generator, the electricity jumps through the air. So that is equal to, just rearranging this, the delta V will be E times delta R, which is D. And putting those numbers in there, the spacing was 20 microns between the plates, you may recall, 20 times 10 to the minus 6 meters. The maximum electric field is 250 megavolts. That's not the standard unit. So it's 250 times 10 to the 6 volts per meter. When you crunch this out, you get 5,000 volts. So our little molar capacitor that we had in this problem, this is what a molar looks like, by the way, that can go up to 5,000 volts before it gets fried. And it has a value of 2 microfarads that is given. And then we calculate the plate area for that. And that's what that area is. So this is an example of a typical capacitor problem. So previously we saw that the potential energy is related to the potential. So this is the potential energy, and this is the potential. And this, of course, is the charge. So we saw that the potential energy was related to the potential by this equation, that U is equal to Q times V. In fact, V was defined as the potential energy per charge, and that's what gives you this. However, this is when you have a fixed and a constant potential. If the potential itself is changing, you need to take the average value. And that's what happens with a capacitor. As you put more and more charge in, the potential builds up. So you need to take the average. So as you add charge to a capacitor, its voltage goes up, its potential goes up. So initially you start with 0, and then you have some final value V, which equals Q over C from the definition of capacitance. So you have a linear relationship between these two. So the average value is half of the final, because initially is 0 and then you have a final value. The average is going to be basically half of the final. So in this previous relationship between U, the potential energy being Q times V, instead of just the final V, you need to put half of V. And this gives you the expression for the stored energy in a capacitor. U of a capacitor is 1/2 CV squared. So let's now do an example for the stored energy in a capacitor. So this particular example is for a defibrillator, as you can see in the picture. So you charge a capacitor to a certain voltage and with a certain amount of charge and energy, and then you basically apply some kind of paddles to the poor patient and hope for the best. So how much is the energy that you deliver during such a shock, basically? So in this particular scenario, the capacitance is 200 microvolts. You're charging it to 2000 volts. So this is 2000 microfarad, sorry, not microvolt. That's the capacitance. The voltage is 2000 volts. So that's the difference between the plus and the minus plate, the difference in potential. And the charge is applied, the current is applied for a time of roughly 10 milliseconds. So these are like typical values. Depending on the situation and the model of machine that you have, they're going to be somewhat different. The question is to find U. How much is the stored energy? So this, by the way, is your first encounter of a circuit diagram. So this thing over here, the two paddle plates with wires sticking out. So every capacitor, a paddle plate capacitor, it'll have two terminals, as you can see over here, a plus and a minus. And in this case, the two of these wires sticking out. And where's that other one? Here we go. So this is the other capacitor that I had. As you can notice that you have these two wires sticking out. So that's what this symbol is meant to represent. You have the parallel plates of the capacitor, and that you need to connect to those plates. So you need to have wires sticking out that you can connect to the patient or whatever, a battery and stuff like that. So this is the charged capacitor. This is a wire that's running out of it. It goes through another, this is a circuit element, basically. It's a device. This is now connected to another device called an inductor. How that works is a subject of a future chapter. And it basically slows down the rise of the current. It makes sure the charge doesn't gush into the heart and basically kill the person. And so this is connected to the heart. This is the wire from the other plate of the capacitor. This is going through a switch. So what's a switch? If you want the charge to flow, you need to connect the wires together. That's what a switch is. When the switch is open, it's called open. That means it's not connected. When the switch is closed, it's connected and the charge will flow and the electric current will flow. So that's what a switch is. It's basically a place where you can make contact or break contact, make or open the contact. And so the other thing is connected to the other paddle going to the patient. And that's what this is. This is an example of a circuit diagram. It has multiple devices or circuit elements connected together by wires. And in this case, the heart and the chest of the patient is set to complete the circuit. The electric current, the charge flows through that. But now getting back to the question, what's the energy that this capacitor is storing and how much energy is being dumped into the patient? So let's see how that works out. So here you have it. The stored energy of a capacitor is 1/2 CV squared. 1/2 is 1/2. The C was 200 microfarad. So it's 200 times 10 to the minus 6. And then you have V squared. So the voltage that the capacitor was charged to was 2000 volt. So 2000 squared. So when you crunch this thing out, you get 400 joules. So this capital J, that's for joule. So that's how much energy in joules that gets dumped in a shock like this. So the last bit of official business is connecting capacitors in series and in parallel. So if you have two capacitors, you can join them like this. So you connect the negatives to the negatives and the positive to the positive. This is called a parallel connection. For obvious reasons, in this configuration, they tend to look parallel. The other way you can connect capacitor is to connect them in series, and that would be like this. So the charge and the electric current goes through this one, goes to the other one, and comes out from there. So this is a series connection. This is a parallel connection. When you connect them in parallel, the capacitances add. Why is that? So here's kind of a diagrammatic view. It's a circuit diagram of two capacitors connected in parallel. You can see each one is a set of parallel plates. So it's like increasing the area. So as a result, the capacitances add. And then the formula for that is the C total is the first one plus the second one. You can have 3, 4, 5 in parallel. You just keep adding them algebraically. So capacitors in parallel, just add. You just add the numbers. So this is similar to joining two tanks. If you have one tank, of water, its area is basically the capacitance. For a certain height of water, you have a certain quantity. For a certain height, you have a certain quantity of water, a certain volume. If you connect another tank to this, then for the same height, you can hold more volume. You end up adding these areas to give you a sense of how much volume you can have for a certain height. And that's what happens over here. So now let's look at the other type of connection, the series connection. So here are a pair of capacitors connected in series. The charge and the current goes through one, and then the other, and then it comes out. So if you look at the formula for a parallel plate capacitor, it's C equals epsilon A over D. If you increase the area, you increase the capacitance because you reduce the potential energy. But D is the enemy. If you increase the space between the plates, you reduce the capacitance. You reduce that canceling effect of the repulsion when you have positive and negative charges together. So if you look at these capacitance series, it's like you have one after the other. Effectively, it's like adding the distance. It's like increasing the distance. So the capacitance will be less. And therefore, the formula for series connected capacitors is you don't add the capacitance. Instead, you add the reciprocals because the D is what you're increasing. That's in the denominator basically. So 1 over C of the total is 1 over C1 plus 1 over C2. And you can have a bunch of these. Just keep adding the reciprocals. And that's the reciprocal of the total. So this one over here, it's a half microfarad capacitor. This is another 1/2 microfarad capacitor. When you connect them in series, you have 1 over 1/2 plus 1 over 1/2. That's 1 over the total. So the capacitance ends up being 1/4 of a microfarad. Starting with 2 half microfarads in series, you reduce the capacitances. So let's put these formulas to good use. Here's an example. You have 3 capacitors connected in this combination. So you have a C1 and C2, they're in series with each other. And then that whole thing, it's in parallel with a third capacitor C3. So you just connect the wires as shown over here. One wire comes in, it splits up, goes to this capacitor C1 and to C3. The other side of C1 is connected to a lead of C2. By lead, I mean these things over here that stick out from those capacitors. Then it goes on, and then these reunite. So the wire coming out from here and the wire coming out from this one over here, they basically reunite on the other side. And this is a combination of 3 capacitors. What's the value of the total capacitance? So going from this end to this end, the whole combination, what's the effective value of this capacitance? So you apply. So first of all, these two are in series, so you can add them using the series formula. Having done that, this acts like one big capacitor, a combined capacitor, which is in parallel with this one over here. So after finding the value of this series, put that in parallel with C3. And that's going to give you the total capacitance of this combination. And here's what this looks like. So apply the series formula to C1 and C2. So the combination of C1 and C2, that's equal to 1 over C1 plus 1 over C2. That gives the reciprocal of the combination C1 and C2. Working this out, each of these are a 2 microfarad capacitor. So 1 over 2 plus 1 over 2, 10 to the minus 6. This gives you a C combined of 1 plus 1 and 2 together of 1 microfarad when you add these together. Now next, so now you have the C1 and 2 combination of 1 microfarad. That's in parallel with C3, which is a 4 microfarad. So this one is 4 microfarad. So once you have the capacitors in parallel, the formula is you add them up. So add this 1, which is the result of combining 2 and 2, and then add to this 1 the 4 microfarads you have here. So the total capacitance of this combination of 3 capacitors is 5 microfarad. And this is how you combine capacitors. So oftentimes you need a certain value of a capacitor. You may not be able to buy that. Like they come in half microfarad, 1 microfarad. What happens if you need 0.65 microfarad? So you basically buy a bunch of these things and combine them in parallel and in series. And this gives you the total capacitance that you need. And this is done routinely. So that concludes the official business for the chapter on capacitor. But I want to leave you with a optional thinker question. See if you can solve this, and a solution will be provided shortly. You have the following situation. You have a huge sphere, which is 1 kilometer in size, if you can believe that. It's charged to 100 volts. Then you touch this with a little lollipop thing. So this sphere is only 2 centimeters, and it has an insulating handle. So you touch this over here, charge is going to flow. So this is a positively charged. Okay, charge is going to flow, and you'll end up with some positive charge on this little sphere over here. It'll acquire a voltage, a potential of 100 volts. Why? When you touch 2 conductors together, you have an equipotential surface, or the whole piece of metal has 1 potential, equipotential. So when you touch this to that, it gets charged to 100 volt. Now we have a third sphere. It's intermediate in size at 20 centimeters. And it's like something like this, the size of a head basically. You now touch this to this metal sphere. So that positive charge is going to flow on here because there's nothing here to begin with. The charge is going to flow, it's going to redistribute itself. So because it has spread over a bigger area, the potential will drop. So this was initially 100. When it touches that, both will end up being, let's say, at 10 volts or 15 volt. Now you touch the lollipop back over here. It gets recharged to 100 volt. You bring it in contact with this third sphere over here. This now has more concentrated charges at 100 volt. This is sitting at the 15 volts or something like that. This charge will transfer to that, and it'll sort of redistribute. This is going to drop down. The third one is going to go up. You'll end up at, let's say, 20 volts or something like that. And you keep this process up. Eventually, the best you can hope to achieve is that eventually all the 3 will be at 100 volt. It's like connecting 3 tanks of water. If you connect them together, they'll end up at the same level. So the best you can do is to charge all 3 at 100 volt. So here's the thinker question for you. What can you modify about this experiment so that this can be charged to more than 100 volts? In fact, practically to an infinite volt. So what can you change about this so that you keep transferring charge from there to there? It never backflows, and it just keeps climbing up and up and up beyond the 100 volt. So see if you can come up with an answer. It has to do with the behavior of charges on conductors and inside conductors. So think about that. The solution is coming up shortly. So the solution is simple. You cut a hole in R3, in the third sphere that you have. Instead of touching it to the outside like this, you make a hole and touch it inside. As soon as you do that, there's a rule. A static charge cannot sit inside a conductor. So once you touch it on the inside, whatever charge was on this lollipop will go to the outside of R3. So when you pull this thing out, it has 0 charge. It's given all of its charge to R3. And as you keep going back and forth, the charge on R3 will climb without limit. It'll keep going up and up and up. It's not going to stop at 100 volt. So this is like if you had the 3 tanks of water connected together. Instead of that, you take water from the first and pour it into the third tank from above. There's no restriction on level. It can keep going to any level basically. And that's how a Van de Graaff generator works.